Hello everyone. Today we will see about Linewaver Burk plot. I'm sure you are all familiar with the term enzymes. They are all biological catalysts, and almost all 100% you can say like that. These biochemical reactions in any living system, it is controlled by these enzymes. And these enzymes or this activity of these enzymes, it is regulated or controlled by various factors. It can be internal or external. And the substrate concentration, each and every enzyme, it is specific, and the substrate concentration of these reactions, it is greatly influencing the rate of the reaction or the turnover number. The rate is usually measured as turnover number. So this substrate concentration will greatly influence the efficiency of an enzyme or its production, or the turnover number. It is influenced by the substrate concentration. And when you increase the substrate concentration, a corresponding increase, it can be seen in the output, that is the rate of the reaction. Now let us consider an enzyme catalyzed reaction. You are going to plot the substrate concentration and the initial velocity. The initial velocity, it is taken on the y-axis. It is denoted by V0, and the substrate concentration, anything in square brackets denotes concentration. So the substrate concentration, it is plotted on the y-axis. And you know, an increase in the substrate concentration will definitely create an increase in the rate of the reaction or the initial velocity of the reaction. So if you plot the substrate concentration against the initial velocity, you will get a graph like this. And if you see, you can see in the initial stages, this graph or this curve, it is almost straight. That means the rate of the reaction, it is directly proportional to the increase in the concentration. When it reaches or when the substrate concentration reaches beyond a particular limit, you can see that plot, it is achieving a plateau, or it is more or less flat. That means the rate of the reaction, it has become steady. But if you look that region very closely, you can see that it is not straight. That means the velocity is not constant. It is gradually increasing. You can see an increase in the rate of the reaction. That means it is not at all steady. And this may appear to be the maximum velocity that can be achieved by this enzyme. But actually the maximum velocity is not this, it is slightly above this, and this dotted line represents the maximum velocity, that is V max. And this V max, it is, you can say that it is a hypothetical value. You cannot achieve the maximum velocity in this concentration. You can achieve the maximum velocity with infinity substrate concentration. And it is very evident from this graph. This graph, that you cannot accurately determine the maximum velocity of an enzyme catalyzed reaction from this graph. And look at this point. This point, you can see that it is halfway to the maximum velocity. It can be denoted by half Vmax. That is the that velocity. It is half of the maximum velocity that can be achieved by this reaction. And if you look at the concentration for attaining that half Vmax, it is represented as Km, and this Km is known as Michaelis constant. And in any enzyme catalyzed reaction, this Km value and this Vmax value is very important. You have to determine these two values. So from this graph, as I have already told, you are not able to find out the accurate Vmax value, and hence you cannot find out the Km value also. Now I would like to invite your attention to an interesting thing. See, you can see a straight line. If you plot the inverse of the substrate concentration and inverse of the initial velocity here, you will get a straight line. And this straight line, it is intercepting, and this plot, it is known as Linewaver Burk plot, and this is intercepting at 2 points on the axis, on x-axis and y-axis. Let us see what are these points denoting. Okay, before going into that, we will see something else. Of course, that is related to our plot. You are familiar with the Michaelis-Menten equation, and this equation shows the relationship between the substrate concentration and the initial velocity. You can see Vmax and Km on the right side, and this Vmax and Km, it is a constant for an enzyme. So here the variables are the initial velocity and the substrate concentration. So this equation, it shows the relationship between the substrate concentration and initial velocity. Let me take the inverse of this equation. Then this equation will become 1 upon V0 equals Km plus substrate concentration upon Vmax times substrate concentration. Now let me split the right hand side of the equation. Then you will get 1 upon V0 equals Km by Vmax times substrate concentration plus substrate concentration upon Vmax times substrate concentration. Now, if you see the right hand side, you can see that the substrate concentration in numerator and denominator, it will get cancelled each other, and I am going to split the first half of the right hand side also. Then this equation will become 1 upon V0 equals Km upon Vmax times 1 upon substrate concentration plus 1 upon Vmax. Can you find any similarity to something else with this equation? Yes, it is something related to the equation of the straight line, that is y equals mx plus c. This equation is the equation for a straight line. So this Michaelis-Menten equation can be converted to something which is related to the equation of straight line. So this y denotes 1 upon v0, that is initial velocity. M is the slope, that is km upon vmax. Then x is the x value, that is 1 upon substrate concentration, and c is 1 by vmax. So this is that equation, and this is the equation for this can be related to the equation for the straight line. Now you know, on x-axis, any point on x-axis has its y coordinate 0. So let us substitute that value in this equation, then you will get 0 equals m times x plus 0. Now let us solve this for x, then you will get x equals minus c by m. What is this c value? C is, you can see it is 1 upon vmax. And what is this m? M is km upon vmax. Now let us substitute that in this equation. Let us see what is happening here. So you will get minus 1 upon vmax divided by km upon vmax. Here this vmax in the numerator and the denominator will cancel each other, and finally you will get the value as minus 1 by km. So that is the x-intercept of Linewever Burk plots. So this point will give you an accurate value of km. That was not possible with our previous plot. Now let us consider the second case, that is on y-axis. On y-axis, the x value will be 0. Any point on the y-axis will have its x coordinate 0. So our equation will become y equals m times 0 plus c. That means y equals c. What is the value of c? Again it is 1 by vmax. So y equals 1 by vmax. Y means that is y-intercept. So what are those two intercepts on Linewever Burk plot? One is 1 by vmax, that is on the y-axis, and minus 1 by km, that is on the x-axis. So by plotting the inverse values of substrate concentration and the initial velocity, that is 1 by v0, you can have the accurate values of these two. That is not possible with the other plot. Okay, so coming to the application of Linewever Burk plot. So by its linearity, here this plot, if you plot the values, that is the inverse value of substrate concentration and the inverse value of initial velocity, you will get a straight line, unlike the first one. So by its linearity, it confirms that this reaction, it is following Michaelis-Menten kinetics. Now coming to the second one, that is, as we have seen, it can determine the km value and vmax accurately. Then third one, it helps in the determination of enzyme inhibition. You know, these enzymes are proteins, and these proteins or these enzymes can be inhibited by various types of molecules. Different types of inhibitors, it can be competitive inhibition, non-competitive inhibition, or uncompetitive inhibition. We will see all these type of inhibitions in another session. So by using this Linewever Burk plot, you can determine what type of inhibition it is done by a particular inhibitor. So these are the various applications of Linewever Burk plot. Hope you enjoyed this video lecture. See you in another session of this biochemistry. Till then, goodbye.